Hello, my name is Claudiu Popa, and today I'm going to talk a little bit about static analysis in Python, especially static analysis with Pylint. Pylint being one of the most comprehensive static analysis tool currently available in the Python world. And just a little bit about me. I'm the current Pylint maintainer, and I'm basically the only contributor at this point in Pylint. Yeah. So, if you never heard of Pylint until now, or about linting or whatever, basically Pylint or a linter is a tool which analyzes your program in order to look for various flows in your program or in your code, looking for warnings or other potential errors you might have. And it's also one of the oldest static analysis tool currently available in Python, being created in 2003 by a French company called Logilab. So basically, it has 12 years of existence, and it's still maintained. Yeah, but saying that Pylint is just a linter is really an understatement, since it can do a lot more than just a simple linter. It's also a style checker, which tries to enforce PEP8 rules. It's also a type checker, and it looks for various type errors in your program, such as adding strings to numbers, or raising objects which are not exceptions, or unpacking too many items in too few variables, stuff like that, basically. And it's also a structural analyzer, looking for various design anti-patterns that you might have in your code, or various implementations, bad implementations of your special methods, and so on and so forth. If you don't use any code quality assurance tool right now, you should definitely try one, not just Pylint, any other tool, because it can really help you, especially when you have a very big code base. Even though you have tests, that doesn't mean your code is perfectly safe, and having an extra step of verification doesn't hurt. Yeah. So let's see some of Pylint's capabilities. So I have this code which does some stuff, and I'm importing the OS module, but I don't use it. I'm declaring a variable called execute, but again, I don't use it. At line 8, I indented badly the for loop right under the array statement, which means that block will never be executed. And to make things worse, at line 10, I forgot to put the parentheses to the execute method. So I have a statement which has no side effect at all. So what happens is that simply running Pylint over this code will emit those warnings, and the developer can go and fix them before they can become real bugs in production. Second, Pylint can be used to detect more serious flaws and bugs, such as if you use undefined variables, or if you're trying to access attributes which just aren't there, or you are trying to call objects which aren't callable. So what's happening is this example is that I'm trying to use a variable which wasn't defined out file, and I'm trying to call an instance of zip file which is not callable. Yeah, and Pylint detects these issues and properly emits a warning, and they can be solved afterwards. It's also detecting less serious problems that can turn to be actual problems in production, such as this case. Basically, I have a function that I'm using to test a condition, whatever that condition is, but I forgot to put the parentheses into function call. So what's happening is that I have an if statement where the if branch will always be taken because the if condition will always be true, because functions have true value in Python. So this is a thing that you can miss actually when doing a review or when you're testing. Yeah, that's a badly written test after all. So it can be used to detect these kind of issues, and not just only that. Pylint actually is not one component per se, in the sense that its business logic is split across two components. First, there is Pylint itself, which is basically the project with the patterns of problems in your code. And the second component, which Pylint is based upon, is our inference engine, basically, Astroid. So Astroid is practically the framework for having abstract syntax trees in Pylint, and it's also an inference engine. If you don't know what an abstract syntax tree is, it's basically a tree representation of your syntactic structure of the code. But ones provided by Astroid are a little bit more capable than the default ones, because they have some capabilities that are really useful, not only for static analysis, but for other tools as well. Yeah, and internally, but an implementation detail, we are using the built-in AST module, but we're trying to move away from that. And we'll see in the next slide why. Because it's not backwards compatible. So it changes from, it could change from one minor release to another, from 3.4 to 3.5. And we need to have a compatibility layer that we can work with from Python 2.7 up to 3.5, and that needs to work on PyPy, on Jython, or any other interpreter. So we're striving to build Astroid to be as compatible as possible. So it has a standard API, basically. Yeah, and Astroid, it's actually pretty similar with the Astroid's API is actually pretty similar with the AST API, in the sense that you give it a string and you obtain an AST afterwards. So this is how an AST looks. In this example, I have an AST for a lambda function, which just receives a parameter called x and returns that parameter with one added, with the value 1 added to it. So it's not really that complicated after all. Yeah. Next. So I mentioned earlier that Astroid has some extra capabilities that the built-in AST module doesn't have. And some of these capabilities, for instance, are retrieving the parent of a node or the children of a node, and this can be really useful if you want to implement your own tree traversal. Yeah. Also, we have a way to retrieve the lexical scope of a variable or a node. And for instance, in the first example, the scope of that assignment will be the module itself, because it's considered to be a module out there. But for the second example, the assignment of 42 to foo, its scope will be the function where it is defined, because in Python, a function creates a new scope. And in the last example, the scope of the foo variable from the list comprehension, at least on Python 3, will be the list comprehension itself, because the variable won't leak outside when the list comprehension finished executing. Yeah, so it's nice to see these kind of capabilities in Astroid. Some nodes actually are augmented with extra features that are tailored especially for them. And in this example, I'm having a class, a couple of base classes. I'm using a meta class, the ABC meta class, and I'm defining a couple of slots. It's not that complicated. Okay. And I could use the slots method of the class node in order to retrieve the slots. So basically, what the slots will be constants, will be strings, as I declared them here. I can also retrieve the meta class of that class, which will be in this case ABC meta. And I can retrieve the method resolution order of that class, which is actually the same method resolution order as if that code was executed by the Python interpreter. And it's really cool to see a static tool doing this kind of high-level understanding of the code. And regarding this high-level understanding of the code, the most important capability that Astroid provides is the ability to do inference. And I don't mean only type inference, because in Pylint we are more interested in what the code does rather than what the type of a variable actually is. So inference basically is the act of solving or resolving what a node or a subtree actually do when executed at runtime. For instance, what a name node represents, or what a function call represents. And in Astroid, each kind of node has its own inference rules according to Python semantics. And we're also doing a form of partial abstract interpretation, in the sense that we're evaluating each statement from functions or from other or from modules or classes, and we're recording what the side effects of each statement will be. So we'll know that at line 5 you're declaring a dictionary, and at line 7 you're updating the dictionary with a couple of other keys and values. So that means that if you access those values at line 6, Pylint can tell you about that. Okay. Let's see a simple example of inference. It's not going to be that hard. In this example, I have the AST of a function definition called add, which receives two parameters, A and B, and simply adds them together. And secondly, right at the bottom, I have a function call of add with two values. In that case, it will be 2 and 3. So what will happen when Astroid tries to infer the function call? First, the callable is inferred according to Python semantics, in the sense that first we'll look into local scope, then into closure scope, global scope, and then in built-ins. If it's not fine, then that's going to be an error. So we'll infer add to be the function that we defined earlier. Yeah, right. Secondly, we're inferring the function arguments of that function call. And in this particular example, it will be actually easier because they are just constants. But if it were names or other calls themselves, they would have been inferred to their end value. Second, each return statement from the function, or each return value from the function will be inferred. That's basically because right now we don't have flow control understanding in Python. So basically we're ignoring every flow that you might have out there, and we just return an union of all return values. So the inference will go to the return value, which is a binary operation between two values. We'll try to infer the name A, which will be the first argument, which is 2. Second, we'll try to infer the B name, which will be the second argument, which is 3. And then we do some other checks before applying the binary operator. First, we'll check to see if the left-hand side of the operation is a subtype of the right-hand side, or it's a supertype, or they are the same type, because almost for every situation in this example, there's going to be different rules for the operation. And in this example, A and B both have the same type, which is an integer, and that means we can safely apply the operator, and at the end, Pylint will know that that's going to be 5. And the inference result will be returned up to the function called entry point, up to the inference entry point, sorry. This is a more complex example involving two instances that are added together with the plus operator. And according to the previous rules, A will be a supertype of B. And that means, first, the right-hand side dunder error add method will be called, and that's going to return not implemented. And if that returns not implemented, then it's going to fall back to the left-hand side dunder add method, which simply does some computation. And if you do this calculation yourself, you'll actually see that the result will actually going to be 45. So it's really cool to see a tool having this kind of level of understanding without actually executing code. Now, this is an example involving some super calls and some complex method resolution orders, and take a couple of moments to see where the problems are. There are actually 3 problems in this example. Why is that?
A microphone, please.
Yeah.
Who wants the mic? I'm going a good way. Which way? I went the worst way possible.
Okay, so the second call to super is saying super C, which is, so you're saying you're ignoring Python's method resolution order and saying that you...
No. We're actually dealing with Python method resolution order. So it doesn't ignore it. It actually respects it.
Okay. Oh, in that case, you've lost me then.
Anyone? Yeah. Yeah, that's one.
Can you repeat that for the mic, please?
I'm only doing this because this needs to end. Foo is not a function,
yeah.
Although it's been called as one, and spar should be spam.
Yeah, that's right. And there's another one on line 14, and let's see which one. Basically, there are too many positional arguments for that call, because super C self doesn't mean the parent of C. It means actually B, because self provides the method resolution order, and C tells us where in the method resolution order, from where in the method resolution order should be looking, and that means in B, and B-boo doesn't accept 2 positional arguments. And finally, a more complex example, which involves a lot of Python's semantics, like variable positional arguments, context managers, slicing, indexing, a bunch of built-ins. And as you can see, Astroid and Pylint can really understand what that code will actually do when executed, which is generating that awesome string. Yeah. And finally, about inference, having good inference actually improves your linter a lot. And we're understanding a lot of Python semantics, but we're definitely not there, and we need to put some more effort into this. Yeah. The real magic of Pylint isn't actually done by Pylint itself. Pylint is just using Astroid, and it's just looking for patterns of errors in the AST, just walks up to tree and tries to infer some nodes and checks what errors can those nodes hide. And it's not a perfect world. It has a lot of false positives, and some of you maybe are hating the tool for this. But we're doing a lot in order to avoid to have false positives in Pylint. Basically, let's say whenever operation with classes are involved, we're looking to see if that class or those classes have unknown base classes. An unknown base class is, let's say you imported a class from a module which doesn't exist. So what will happen is that if that module would have existed, then that class could have some extra capabilities that are unknown to Pylint at that moment. So the safe path is just to ignore those classes. And we have to check very often the state of the inference and every inference result. And if you see that the inference failed, we have to skip the check and go to the next one. So there's a lot of effort in avoiding false positives in Pylint. And even these extra verifications aren't useful when you're dealing with dynamic code, such as globals or patching stuff at runtime, or whenever you're working with extension modules, which are basically written in C or some other language, and you can't statically analyze those, and you have to import the module, and you have to work with live objects. Also, when the code you're supposed to understand is too smart, is relying heavily on meta-programming techniques, on meta-classes, descriptors, whatever. And actually, this can be a corollary. If your code can be easily understood by a static analysis tool, then most probably that code is going to be hard to understand for your colleagues, for your human peers. And these are some examples of actual code that is expected by some Pylint users to be understood. Yeah, we have basically list comprehensions, putting stuff in vars, which will be globals, because that's at the module scope, patching under all at runtime. And secondly, in multiprocessing, we have that globals update. And that's really hard for any static analysis tool to comprehend properly. There's a lot more that you can do with Pylint. You can actually define your own plugins if you want to. There's a bunch of them for popular libraries like Flask and Django. You can actually, there's a checker which you can use to spell check your comments or your doc strings, which uses the Python enchant library. There's also a Python 3 porting checker, which is activated by --py3k flag, which just deactivates all the other checkers and emits warning in your Python 2 application regarding Python 3 compatibility. And let's see an example. Basically, in this example, I'm using a bunch of Python 2 features, like declaring the meta class of a class by assigning it to the dunder meta class attribute. I'm also declaring dunder set slice, which was removed in Python 3. And I'm relying on the fact that map is eager evaluated, which is not the case in Python 3. So in Python 3, that map call will just do nothing. You have to evaluate it, being lazy evaluated. And yeah, just activating the Python 3 porting checker, and you can see those failures and fix them. So it's nice to put it in your CI if you have a Python 2 project in order to verify that you don't regress for Python 3. And there's a lot more to come in Pylint. We are planning to have Pylint 2.0 next year with a lot of cutting-edge features, such as full flow control analysis, which includes also data flow analysis. Also, we are planning to have a better data model of the Python world, and support eventually type hints, PEP 484. And I'm also planning to build an abstract interpretation engine that's going to be separated in Python. So Pylint will just become an implementation detail or a use case, basically, of that tool. And hopefully, I could bring more contributors into the project. And I think I'm done. Are there any questions?
How does the inference engine know to evaluate objects and when to, like when you're looking at two inches, you add them together, but how do you avoid side effects, or what does it decide to evaluate, kind of thing?
Oh, I see. I'm not sure, basically, because we are looking for side effects only for things that we know that they will have side effects. For instance, the update method of dictionaries. If you use that, we'll know that that's going to be a side effect function, and it's going to change some other object. But in general, we don't know. We have to hard code that information.
First off, thank you, because I think Pylint is amazing, and I can't imagine programming without it these days. So I recommend it to everyone who I recommend Python to. I was surprised when you said that you were the only kind of major contributor. So I did just a quick web search on my phone, and I couldn't help noticing you're based on Bitbucket.
Why what?
You're based on Bitbucket, the project?
Yeah, you're using Mercurial.
Yeah, I mean, I like Bitbucket. The other day I had to kind of clone something from Bitbucket, and there was just this little, because everyone's on GitHub these days. Yeah. There's just this little threshold that was annoying, and I can see that might discourage people from joining or contributing. I'm just suggesting it, because it was a standout, that was all.
Yeah. Okay.
When you have objects like files or sockets that need to be opened and then closed, is Pylint able to analyze this and tell you didn't close your file?
No, but we can have a checker for that. I mean, it's can be easily implemented in Pylint. Okay. Are there any other questions? Okay, thank you.